In this video, we're going to talk about a diagnostic tool regarding the least squares regression line, and this is with a measure called R-squared. It has a more official name. It's called the coefficient of determination, but most folks really just call it R-squared. Now, we've seen the letter R in a couple videos ago where just regular R is the linear correlation coefficient, and R can be between -1 and 1 because the linear correlation coefficient describes not only how strongly two variables are associated, but that sign, positive or negative, tells you the direction as well. The R-squared value is just the square of whatever R is. But what it accounts for is the amount of variability in the response variable that can be attributed to or accounted for by the explanatory variable. Another way to think about that, like up here, this is the official definition, but another way to think about that is R-squared provides you some indication of how well your future outcomes are likely to be predicted by using that line. So R-squared can be as small as a 0. And we'll talk about what 0 means, but it can go all the way up to a 1. Let's talk about those values, those limiting values. If R-squared was a 0, that means that the line, the least squares line, has no predictive power, that the variables are not correlated, and therefore using one variable to predict the other is useless. So an R-squared value near 0 has no power. On the flip side, as good as it gets, if R-squared equal 1, then the least squares line explains all of the variability that was observed in your response variable. Let's look at a couple limiting examples here. On the left, I've drawn a little scatter plot. Can you imagine what the correlation coefficient would be here? Is this a negative or positive correlation? Negative, right? And it's a perfect correlation. So this would be a -1. R-squared would be a positive 1 because based on this sample data, if you change x, you know exactly what to expect and why. Right? Because look how perfect it is. So you would feel very good about the predictive ability of this line to make predictions about y based on x, because the line accounts for all the variability in the response variable. Let's look at another scenario. On the right here, what I've tried to illustrate is a scatter plot in which the two variables have very little correlation. So R near 0. Because the variability in the y values doesn't seem to change based on x, right? As opposed to the scatter plot on the left, you change x, y is coming down. Change x, y is coming down. But over here, if you consider different values of x, there's no idea on what's happening in y. The least squares regression line here would be a horizontal line, most likely. No correlation between these two variables. As such, there's no predictive power in such a scenario. So the r squared value would also be near 0. From the previous video, we saw the cars data set, which was a relationship of distance on speed, and we had the slope and intercept estimates here. If we were to write the equation of the line, our slope estimate, 3.9324 times x minus the 17.5791. So that is the equation of the least squares line. And we can use that to make predictions for distance based on speed. Here we see that the r squared value is about 0.65. So to me, one of the easiest ways to kind of consider how good our predictions will be would be about 65%, because that's the r squared value. So let's make a prediction. I'm going to make this a little bigger. So let's predict the distance if the speed O is, let's do 15. So we are given a value for x, which is 15, so we can plug that into our equation of the line. And this will be the predicted y value. Even just looking at the graph, I should have expected a number near 40, right? Because 15 on the x going up to the red line appears to be about a y value of 40. So we have a coordinate on the line of 15, 41.4069. This is a coordinate on the least squares line. Right, that is not data. It's not data, right? Because it's not one of those 50 observations. This is a predicted value of distance for the speed of 15. And something fun that we can do is actually put that coordinate on the graph so it's easy to see. I believe we can do that with the points function. So we just want to plot the point 15, 41.4069. Now if I just plot it, it's going to be almost indistinguishable from all the other observations. Let's take a look. I'll put my cursor there, and here we go. Whew! Okay. So that's hard to distinguish from all the other circles on the image. So let's give it a different color. I'll choose green. And now it stands out. You could even give it a different symbol, a PCH. And there's lots of different options here. I'm going to choose 7 because I know 7 will be a rectangle or square, and that is much different than all the other circles. Back to r squared for a minute. Got off track there. Because we see this linear relationship between x and y, knowing information about x gives us information about y. And the value for x will influence the value of y. However, if you did not know what this relationship was, and you had to predict y, but you didn't know what this line was, or this image, you could still make a prediction for y, right? Without knowing any better, wouldn't your best guess for the distance, wouldn't it just be the average distance? Because if you didn't know the impact x has, you're just in a box somewhere, your best guess is to use the mean. So R squared is an indication of how much better your estimation is going to be by using the information you know about x to predict y. Another aspect about the validity of our predictions is whether or not we met the requirements to perform linear regression. So let's talk about those requirements. For every hypothesis test that we've done, there has been some need for random sampling from the population. And there's a lot more details to this provided in the textbook, but I will leave it at that. Furthermore, each ordered pair needs to be independent, right? So when I say ordered pair, I'm referring to x1, y1 being independent of x2, y2, and so forth. We've seen that requirement in the past as well. So random, independent. Do you remember other requirements that we've seen? There's a normality requirement, right? And here the normality is in regards to the residuals. Residuals are normally distributed. It was in the previous video, maybe the first video, that we defined what a residual is. Remember, it's the observed y value minus the predicted y value from the line. I'm going to show you how to visualize that in just a moment. And lastly, the residuals need to have a constant variance. Constant variance. There's a cool word that means constant variance, and that's homoscedastic, and I think that's just a fun word to say, homoscedastic. And what that is saying is that, okay, these residuals have a constant spread, so the standard deviation does not depend on x. I'm going to show you some imagery that will help interpret that. Okay, I want to show you a couple images from the textbook. This is going to be from page 507 and then page 523. So this first image here isn't actually about the requirements, but I think it helps in considering what those look like. And for a particular x variable, that the observations need to be normally distributed for the x variable. It's kind of almost like a three-dimensional image here. And if x is normally distributed across the domain of those x's, then you're going to have residuals that are also normally distributed. This next image I want to highlight on page 523 of our textbook shows what these residuals look like if they are normally distributed, right? With that QQ plot, we would see an approximate straight line. So this is if the normality condition is met, then you would see the residuals look roughly like a normal distribution. Finally, to show you an example of residuals that have a constant variance or do not, I'm going to go to page 526. So these residuals need to have a constant variance. So the spread in them doesn't change in any critical way depending on x. Let's take a look. So here there's actually a bunch of images, and On the left is the original data, X and Y, plotted. And on the right is the residuals plotted. Now, one of the most striking ones that I want to point out is actually this one on the bottom here, figure part C. What you'll notice is the observations sort of fan out. About the line, the spread in the observations increases. So those are the residuals getting larger and larger and larger as X gets larger. So image part C here matches image part B. You'll see here that the residuals are 0 and they get bigger and bigger in magnitude. Another issue with residuals is if they have a pattern. And here, this top right image, there is a pattern. It's almost like a parabola, downward facing parabola. And that is going to match up with the graph of XY in plot B here. So, and then by elimination, we have A matches with 3. So these residuals are graphed on the right side here in what's called a residual plot. And a residual plot will magnify potential issues in your data that might make the inferences from regression invalid. So what a residual plot looks like is, as you saw, it's a scatter plot. But on the vertical axis is the residual being plotted, and it's usually about 0 because you can have positive and negative residuals, and it's usually plotted along the same x-axis. I'm going to open R again, utilize our cars data to show you these residual plots. So you might remember that way up here, when we did the linear model, we called it model. I can actually plot some results from the model output. Now, I have to do this kind of cautiously because notice what R is going to do. It's actually waiting for you to click on the graph because it's actually created 4 images. So here's our first image. It's got the residuals against our fitted values. It does kind of seem like the spread in them does increase a bit. Going into depth about that is a little beyond the scope of our course, but notice R is still waiting for me to click again. Here is the normal QQ plot. Looks like it's following a pretty good straight line there. Click again, and this is another type of image. It's got the residuals, but it's actually standardized, so that's pretty cool. And another type of image, I'm not going to go into detail about that. So that can be a little complicating there. There's a nice way to graph those into a single image. If I type par mf row equals C 2 by 2, it's going to create a skeleton of sorts, kind of a 2 by 2 trellis for those 4 images to be plotted. So nothing graphed yet because I didn't tell it to graph, it's just kind of got the skeleton there. But now I can ask to plot the model and it'll put all 4 images in that nice little 4-pack. You do have to be a little bit careful here because now if I plot anything else it's going to plot within that 4-pack, and it's really, really small, right? So if you want to graph again, you have to just close that down and start from scratch, so that way you're not constricted to that 2x2 little zone. So regression, we saw we need these random independent sampling design stipulations. We've seen those a lot. We still have a normal distribution requirement, but this time it applies to the residuals, so that's kind of cool. And also that the variance of those residuals is constant. We usually inspect that with residual plots. Putting all of this together, there are these requirements for regression that we need to consider for the inferences from linear regression. The R-squared value is an indication of the predictability of the regression line. And in the previous videos, we saw how to determine the slope and intercept, and if the slope is significant.